Okay, I'm probably going to go into more detail in this problem than the viewer might want to see, but here we go. This problem, finding the limit of the sequence arctan of 15n to the fourth, whether it converges, diverges, find the limit if it converges. I'm going to use a slightly easier sequence for starters. A sub n just equals the arctangent of n, and see where that leads us. And what this means is that a sub 1 is the arctan of 1, a sub 2 is the arctan of 2, a sub 50 is the angle that has a tangent of 50. And here's a table that I created on Desmos where I have a sequence from 1, 2, 3, 4 for the n value, and arctan of n. It looks like it's not growing without bound. It looks like it's approaching some kind of limit here. And the unit circle is a good place to start to see why we think the limit actually is pi over 2. If I wanted to construct an angle in the first quadrant that had a tangent of 50, that means that y over x would have to equal 50. And if y over x equals 50, then y equals 50x. Which means that I would have to have a triangle in here where the y value was 50 times bigger than the x value. So I could probably picture, I wanted to go to black, like a triangle up here. And maybe that y value right there is 50 times bigger than that x value. But what if I talk about a sub 1000? What's the angle that has a tangent of 1000? Well, I would have to get really close to, this angle would have to be coming up this way to get a tangent of 1000, because I need the y value, the horizontal or the vertical component at this point on the unit circle, to be 1,000 times bigger than this little x value. So it looks like as n gets bigger and bigger and bigger, that this angle that has that value as a tangent has to be getting closer and closer to pi over 2. And that's actually what's happening. So that's what we call inductive reasoning. We're looking at some specific examples, and we're kind of drawing the conclusion that perhaps the limit is pi over 2, but this diagram doesn't really prove it. And so here is the definition of a limit of a sequence. If a sequence has the limit L, which in our case we are surmising is pi over 2, if the limit of that sequence as n approaches infinity is L, then if you give me an epsilon greater than 0, and usually we think of epsilon as being a very small number, then there exists a positive number capital N such that when n, which is the number of our term in the sequence, is greater than this positive number n that we found, that the difference between our sequence, in our case it would be arctan of n, minus the number that we think is the limit, the distance between those two will be less than epsilon. What that means is that as n gets bigger and bigger and bigger, the terms of the sequence get closer and closer to L. And I can get them so close that they're less than epsilon. So if you give me a very small number epsilon, I can find a number n so that when little n is bigger than big N, that the difference between pi over 2 and a sub n, or arctan of n, will be less than the epsilon that you give me. Okay, so we're surmising that this limit is pi over 2. Here's how I show it. If the difference between arctan of n and pi over 2 is less than the epsilon that you give me, I want to manipulate the way this looks to find the value of capital N that will give me a difference that's less than epsilon. So if the absolute value of this is less than epsilon, then and epsilon is a positive number, that means arctan of n minus pi over 2 has to be between negative epsilon and positive epsilon. And then if I add the pi over 2 to both sides, arctan of n has to be between these two values right here. If I take the tangent of all three parts, I'll get the tangent of pi over 2 minus epsilon is less than the tangent of the angle that has a tangent of n. It will just be n, and then I'll get this over here. And I want to focus on this part right here after taking the tangent. The tangent of pi over 2 minus epsilon has to be less than n. So n is greater than this value here, so I'm going to let n equal the tangent of pi over 2 minus epsilon. So as long as n is greater than big N, or capital N, then this statement right here will be true, because all I have to do is work backwards to end up here. Okay, and let me go to Desmos and show you sort of what this looks like. Because I want to show you this is like our epsilon right here. N is going from 1, 2, 3, 4, 5, 6. That's forming the sequence. Here's our sequence definition, arctan of n, and you can see that these values are getting bigger and bigger as n increases. And the difference between arctan and pi over 2 is getting smaller and smaller. And I'm going to scroll all the way down to here. As like n hits 50, arctan of n is 1.5507, and the difference between that value and pi over 2 is getting very small. By the time I get to n is 622, I'm at 1.569, and there's our epsilon, or our epsilon. So as I make epsilon, you give me an epsilon, very small, and we're letting capital N equal the tangent of pi over 2 minus our little epsilon. We're suggesting that as long as little n is bigger than capital N, which is 30.28, that I will be the difference between arctan of n and this epsilon and pi over 2 will be less than this epsilon right here. So let's look in the table at what 31 is. I'll bet 31 has an epsilon that's less than 0.033. So where's 31 in the table? There's 31. 0.032 is less than 0.033. And so here's a picture of the elements of that sequence. Starting at 1, you can see that they're getting closer and closer to, this is actually the line y equals pi over 2, which is about 1.57. Okay, and I could add 1,000 in here, and you can see that pi over 2, 1.5707, I'm getting closer and closer to pi over 2, 1.5702, 3,000, and look at how small epsilon is. Okay, so that's the idea behind this. And for your problem, it doesn't matter all this does is make the parameter arctangent grow quicker. So we will get to closer and closer to pi over 2 much more quickly in our sequence. So I'm going to send you the link to this URL, but I want you to see how I have a table here, and there's the limits of the sequence, and already by the time I'm at 4, I've got 1.5705. So very close to pi over 2. After by the 4th element of the sequence, and that's because 4 to the 4th is times 15 gets very big very quickly. Okay, and I just want you to see that you can highlight and unhighlight the elements of the sequence by going to this table right here. And you can also just hide the whole thing by clicking there. And there's problem number 9. Okay, so the limit is pi over 2. If I wanted to actually prove it using the limit definition, I'd go something like this. For any number epsilon, the arctan of 15 n to the 4th minus pi over 2, we want that to be less than any epsilon that you give me, and I'd like to solve for n in terms of epsilon. So we would put this expression right here between epsilon and minus epsilon, add pi over 2 to both sides, take the tangent of every term, divide by 15, and then take the 4th root. So no matter what epsilon you give me, I can find a capital N such that if n is greater than capital N, this statement will be true. Okay, I don't know if you're going to have to be able to do that, but you do have to know that arctangent is based on the fact that as these angles get closer and closer to pi over 2, the tangent gets bigger and bigger. So the limit of this sequence is pi over 2. Okay, so I'm going to end this video and have separate videos for the other 3 problems.